Mic is not on.
Ian? Oh, is this one on? Oh, I can introduce myself. Do you want to talk on this one? Talk on this one. It's clearly working.
All right, so for the next talk, we have Ian on stage. He's founder and one of the core organizers of PyData London, and he's going to tell us about diagrammatic diagnosis of data. Please welcome Ian.
Thank you very much. Good morning, everyone. If I stand here and talk, is that loud enough? Yeah? I can't really hear it, so good? Yeah? All right, that's a good sign. Yeah? All right, perfect. If you can't hear me at the back, then wave or shout or something, and I'll lean in or whatever. So yes, I'm talking on the diagrammatic diagnosis of data, and I like alliterative titles. If you've come to my talks over the years, you would have noticed that. So who am I? I'm a senior data science coach. I work in companies helping them accelerate their data science teams. So I've gone through lots of years solving data science problems. I still solve data science problems. But now I try to make teams more efficient as data science grows in prominence in organizations. And as a result, I try to look one level up from solving the day-to-day problems that a team might be facing and look at the process that's going on around it. And some of that process thinking is reflected in this talk and the tool that I'll talk about right at the end, which solves, I think, a little bit of the process, a little bit of the gap that I see out there. I wrote a book with O'Reilly, High Performance Python, several years ago. Some of you probably would have had a copy of that because I've given away lots of free copies here at the conference over the years. And as Marco said, I was one of the co-founders of PyData London, and we've grown a wonderful team in London running that meetup and the conference. How many of you have been along to our PyData meetups or the conferences? Brilliant, right, a whole bunch of you, excellent, right. And the rest of you should come along as well. It's a really nice event. There's also PyData in Cardiff and Bristol and Edinburgh now. There's over 100 meetups around the world. So please come and get involved in the PyData ecosystem. Consume first of all, and then think about contributing back and give a talk. Over the last couple of years, I've spoken on diagnosing machine learning and using random forests here at the conference. And if you go on my blog, you'll see all of those past talks. So, question for you. Have you ever been asked, sight unseen, I've promised, I'm your manager, I promised we're going to give an answer next week to the client. Here's the data, no one's looked at it, but you're going to give me the answer that I need next week. Go. Have you ever been asked that kind of question before? And hands up if you have. Right, it's fairly terrifying, and we know that when no one's looked at the data's probably awful, and yet you have been promised to deliver a result a week later, and that's a rubbish situation. I've had that too many times in my consulting career, and it's awful, and no one wants to believe that the data might not be perfect and great. And I've spent a lot of time thinking over the years about how do we try and de-risk that end of the process to make it more likely that I can deliver a result that's useful, or at least guide a client. This is a stupid investment in our time. We shouldn't be doing this. Let's not waste a lot of time. And I've got this hypothesis that there are more engineers at a PyCon UK conference than data scientists. It's a pretty safe hypothesis. It's been true every year, but I'm curious again this year. So I'm going to ask you if you self-identify as a Python engineer or a data scientist, and just broadly split you in that very simple way. Put your hand up if you self-identify as a Python engineer more than a data scientist. Okay, that's the majority of the room, fine. So this talk is aimed at you, and for the data scientists in the room, it's a little bit more engineer focused than a stronger data science talk that I might give at a PyData event. So another one. So yeah, we're going to cover these tools with a bunch of visual examples over the next set of slides, and then this Discover Feature Relationships tool that I've written, which I think solves a little bit of the puzzle right at the end, and I'm introducing that in the hope that I get some feedback from you. And then we wrap it up with this notion of a data story, a way of presenting these things that we might visualize to tell a story to our colleagues and to a boss perhaps to say why this data is good or isn't so good and what we might do with it. So Google Facets, anyone used Google Facets before? Anyone come across it? Okay. One. Okay, great. So good start. Google Facets, it's an open source tool. It looks like it's a bit of a pain to install, but Google provides a handy demo online. You go there, you upload some data, and you can start manipulating your data in the browser. So as long as your data could be shared, I don't know what the privacy arrangement is with the public demo site, but as long as you can upload your data, it's an easy way to go and investigate it. It takes any raw data that you throw at it, so a CSV file containing text and numbers. It doesn't really care. You throw it in, and it starts to visualize it. So it's kind of a poor person's Tableau, and it's just available online. You can just throw your data into it. This is the very simple overview. You upload some data. This is the Titanic Data Set. A lot of you are probably familiar with the Titanic Data Set. So that's the list of 1,000 or so people who were on the Titanic ship when it went down, and it records their name, their social class, first, second, third, their age, the amount they paid for their ticket, and whether they survived or died, and a bunch of other details. So it's a mixture of numeric data and text data, and then there's some feature manipulation you do on it to turn it into a machine learning competition, and it's one of the entry competitions on the Kaggle competition website. So you can upload that, it's a CSV file into Google Facets, and you get this kind of display. So you see we have some things like the top row survived. That's the Boolean indicator. Did someone survive or did they die? True or false, so 1 or 0. And it shows it up as a numerical field, but with a histogram of zeros and ones being counted. P class, that's the social class, first, second, and third class. First class rich people, third class in the hold. And then the counts of those. But then we get a distribution that's more continuous, like the age distribution there. So we see a histogram of age ranges. And so it tells us something about this, and we get some red call-outs, so a number of zeros. Maybe that's maybe you don't expect zeros in some of your columns. With age, 20% missing data. So 20% of the age column is missing. What do you want to do with that? You need to do something with it because this data's missing. If you look at a new data source and you've been told, hey, the data's all complete, everything's filled in, and you discover there's a high prevalence in some of the columns that things are missing, and those things that are missing are suspicious because, hey, you think these things should be there, that gives you immediately a way to go back and ask a question. Why is this data missing? What do we do about it? Is it a mistake? Is it systemic? Is it something we just have to learn to deal with? But at least we know to ask that question. So Facets gives you an easy way to at least visualize that. At the beginning, and then we can start to build up some relationships. We get a 2D relationship here. Here I've coloured, can I zoom out? Yeah, you can just about see that at the bottom there, I think. Coloured red is for people who did survive. Red represents 1. So a minority of people survived, a majority of people died. They're in blue. And so we've coloured, and you can't see it here, but all of those circles have some text in them, and that's some of the text field associated with each of those data points. So we get a 2D representation, and we can go further. Here's a 4D representation, and 4D is 1 dimension too many, definitely, but a 3D plus a bit more. So here we've split by the sex column, that's the categorical male and female, still coloured red for survivors. So if you look at the female column on the left-hand side, the majority of people, the majority of the women survived, and the minority of men survived. So we can see that there's some kind of predictive relationship straight away. There's an interesting relationship in the data, at least. And I've also broken this down by age range. So I just selected these different columns, and then the Facets tool put this together, broken down by age, and we can see that for men across the age ranges, pretty much everybody dies, apart from not null, but the second row up, the age of 0.4, so a couple of months to 8 years. So very young male babies, there was a majority survived. So age as a predictive feature has some use in this problem, but sex is the most predictive thing. So we can start to visualize some interesting relationships, and I've annotated every data point with a 1, 2, or 3, which is the social class, P class, and if you select a variable, you get that item on the right-hand side showing all of the actual raw data from the CSV file. So this is a nice, easy-to-use tool that gives you a simple way to select and group your data and get a very visual, interactive output, but it's limited because it's non-programmatic. So it's great just to chuck your data into it and start to visualize it. It can take some quite large files, but then you're very limited after that. And of course, what you want to be doing is working inside something like Pandas. So a lot of you know Pandas. How many of you use Pandas regularly? Right, yeah, okay, brilliant. So we've got Pandas. Here we're going to go a tiny little demo that Mark Garcia gave at our Pi Data event recently with a pivot table and a bit of styling. So here we can do programmatic work on our data. We load in the same data. We've got missing data in the age column. So we're imputing that missing data with the median, we're taking the median value to generate a new column, a new feature, age underscore. And I've generated a new feature as well, has family underscore. So if there are parents and children or siblings and spouses associated with a person, turn that into a Boolean. If they're traveling with anyone, they have family. If they're traveling with no one, they have no family. And we can use that for some further diagrams later on. So then we're going to augment this data into some bins. So we're going to cut the data on this new age column by taking the min value, so that's 0.4 age, through to 18 years, that'll be a young person. 18 to 40, that'll be, I called it a child, young person, and then over 40, an older person. So we label up the data with a cut. And then having done that, we end up with some new columns in our data frame. So we can see the survived, P-class, and the age labeled, this new bit of labeling we've added. And then we can start to do things like a pivot table, pivoting on whether someone survived or died by their social class and the age that we've labeled. So we get this little two-dimensional chart, which is quite nice, but it's a bit hard to read, right? So we've got this floating point number. It's not really a percentage that we might show to somebody else. So we can apply some styling. So here we can make the 87.5 look quite nice. So children in first class, 87% survive. So it's brilliant. We're beginning to tell a story here, but it's still not very visual. We can then start to do things like apply highlighting. And there's a very rich page on styling that you can do inside Pandas. So here we're highlighting on a row basis for each row which class had the highest survival ratings, and unsurprisingly it's first class passengers, be they children, young people or old people. So we begin to tell this story diagrammatically, which we can put into some kind of report. Still not super visual, but we're building this up. So the obvious benefit here over Google Facets is that we can do this in code and generate new data as we go, cleaning up our data and generating a reproducible report rather than using an external tool and taking screenshots from it. This gets us to Pandas Profiling. Who's used Pandas Profiling before? Okay, not enough people. So Pandas Profiling, super useful tool. You take a data frame, a Pandas data frame, put it into Pandas Profiling, and you get a report like this, which becomes an artifact you can add into your repository. So it's a generated report telling you some summary statistics about each of the columns in your data frame. And if I starts off like this, and we can toggle details. This is the age column, and it generates a whole bunch of reports about each of our columns, histogram, extreme values, and then if I get rid of that, we can scroll down and we can see all of the other columns in our data set generated as an HTML report that becomes an artifact that we can add into our repository, including all of those new columns that has family, the age labeled, and then the age imputed column that we've added. So a whole bunch of new reported information that we can share and talk about in a report generated in one line of code. So that's super, super useful. And then that second example to file puts out to a report. Who's used Seaborn? Brilliant. Okay, so a couple of years ago, no one had heard of this thing, and it's brilliant. I'm glad a bunch of you are using it. More of you should be using it. Seaborn sits on top of Matplotlib and gives you better statistical visual reporting, and it integrates with Pandas data frames. So you take a Pandas data frame, you've manipulated it, you've done something, you have, for example, generated a pivot table, but you want to generate that as a diagram. Seaborn takes care of that. So here we have one of the simplest plots. It used to be called a factor plot. In the 0.9 release, it's changed. It's now a cat plot. So we're going to plot likelihood of survival by social class for all people. And so unsurprisingly, first-class people had a better chance of survival, second-class people had a lower chance, third-class people, that's about a 25% chance of survival. It's pretty awful. You didn't want to be third-class on the Titanic. So we get a visual display, and then I've put up a title there, Survival Rates by P-Class. This title deliberately doesn't give us any interpretation, but the subsequent titles give us some interpretation of the data that we've got. But you could imagine this being a part of a descriptive process in a data report. But what if we want to delve a little bit further and look into those ages? So here we're using the age labeled field that we generated before, and then you can see on that cat plot I just passed in a new hue parameter, give it age labeled, and then we get 3 lines. And then we can see indeed that young children first class out-survive by percentage everybody else. And it's always the case that children out-survive middle-aged and older people per social class. And we see that rather than in a table where we have to think about the numbers, we see this nice line plot with an easy slope. So it's nice and easy to interpret. And then the title, younger people generally have a higher survival rate. So it's an easy way for someone who's not a data scientist to interpret the data in a visual form. We might ask some other questions. What about survival rates by sex, so women and men by social class? And again, the same thing, women out-survived men, and anyone who is first class has better rates of survival than second and third class by sex. And that has family feature that we generated as well. If you travel with a family, you out-survive people who travelled alone by social class. So these are things you might do statistics on and generate some kind of terse reporting. But really, it's this visual display that helps bring that story to life, and particularly to communicate it to people who are looking at a report and just looking to understand what this data is that we've got and what we're going to do with it. So we can visualize pivot table-like results that we've generated in just 1 or 2 lines of Matplotlib and Seaborn code inside the notebook, and can show up to 3-dimensional relationships very easily with a couple of these group bys that happen automatically for you by Seaborn. And it's really easy to use, and I super encourage you to try Seaborn. I'm going to give you 2 more sets of examples of Seaborn, and then I'll show the tool. So the Boston data set, unlike the Kaggle classification challenge with Titanic, Boston's about a regression problem. Can you understand housing data from Boston and predict the median price of a house given some social and environmental characteristics? So it's a housing price data set. So this is what the data looks like. You get a whole bunch of columns. It's from the 70s or 80s, back when big data was 500 rows of data. And so we get things like pollution with NOx, RM is rooms, number of rooms in a house, CRIM, the crime index, the amount of crime in the area. So we get a table, terribly undescriptive. We can do a scatter chart. So here I'm just using the plot method in Pandas. Take 2 columns, LSTAT, the low status percentage. So it's the scumminess of a neighborhood. How many low class people are there? I don't know how they measured that. Against median value, so the median price of the houses in those areas. So we can see this kind of interesting banana-shaped relationship. If the LSTAT is low, so if the low status percentage is low, lots of high class people, few poor people, then the median value of your house price is high. And then if your LSTAT is high, so 30%, lots of scummy people, then your median house price is low, and you get this kind of banana-shaped relationship. What we can't see in here is the density of the all these points, because these points just overlap in the middle. So we don't know what's happening in there. One way we can address this with Seaborn is to use a joint grid and put in place these little tick marks to show the density of points, 1 tick on each of the axes per data point. But you still can't really see where the density is. You can start messing around with the alpha values and try to blend things together, but it's still not super clear. But then Seaborn provides even more plots, so things here like the hex bin plot, where each of those hex shapes just counts up the number of dots from the scatter plot before that are inside it. So it's summarizing exactly the same data, but with a clearer visual display. No need to mess around with alpha values. And on the margins, you get the distribution showing the number of points in each of these each of those areas of the histogram. So we get a good idea as to where the density is in this chart without having to start messing around trying to refine our plot. And these things will come for free in Seaborn. And the other thing that I really like in Seaborn is pair plots. And this was brought up by Gael Verrequar at our PyData London conference earlier in the year. And his slides have got loads of extra stuff. You want to go and follow these slides. So with a pair plot, you give it a bunch of columns and just say plot each column against each column, so each feature against each feature. And then we can see top right corner, that's LSTAT versus median value, that banana shape. But we get other things like, so LSTAT versus CRIM. And it looks like maybe there's some kind of positive relationship here, but we're not really sure. There are lots of data points, they overlap. We don't know if there's really some meaning behind this. and you see it's symmetric with these scatter points A versus B and B versus A. And what Gail pointed out is that you can put in place a contour plot on one side. So the bottom triangle is a contour plot showing the density, and then the top plot being the scatter chart. So then we look at this LSTAT versus CRIM. If we come down here, LSTAT versus CRIM, the mirror point, and look at the density. So what is the contour plot telling us about the density? Well, actually it's saying there's no positive relationship at all between these two columns of data. And that's just a visual artifact that we see here from these scatter points that are infrequent against the majority, which are plotted against just the one line here. So that's kind of informative, I think, and that again comes for free, and you can start customizing all of these things in Seaborn. So I've been thinking a lot over the years about how it is that we do this process faster. It's great that we can visualize these relationships if we know that they exist. It's great that we can make artifacts, like with Pandas Profiling, and notebooks that document these relationships, but how do we find the relationships in the first place? So I've been asking myself the question, well, how do we automatically rank and rate things that look like they have interesting relationships in the data, separate perhaps to, say, a target column in a machine learning challenge where we want to know which features map onto that target, but which features interact with other features in the data? What are the dynamics in this data set that I've got that drive all the relationships that are going on? And so I've prototyped a tool. I'll show you a couple of shots of it here. I'm very keen to get some feedback. So first of all, this is an output from the tool. I've just asked it, what's the Spearman rank relationship between all pairs of features? And this comes out of many tools. It's built into Pandas. It's not super interesting, but I thought it set the scene. So here for all of the features, so it's 15 or so in the Boston data set, what's the relationship, positive and negative, between all pairs of features? So age against zoning, criminal against zoning, and all the like down here. But these are symmetric, so it doesn't tell us anything about which feature better predicts another feature, and I think that's an interesting question. So if instead we rerun it with a random forest, we can then see that we get a non-symmetric relationship in this heat map coming out. So here, for example, CRIM predicts RAD, which is radial distance, I think, to highways. So criminality predicts this RAD feature for some reason, but if we look at the RAD feature, it poorly predicts CRIM. So it's a one-way relationship, not a symmetric relationship, which we don't get from the rank correlation plots that we normally get from Spearman and Kendall and Pearson, which is a standard way of doing data analysis. And I think highlighting these one-way, not two-way relationships is interesting because it begs the question, well, why does the data predict in one direction but not in the other direction? And then we can plot the data, and it turns out the reason it predicts in one direction and not the other is because one of the columns, RAD in this case, has been heavily capped. There's a whole pile of data points capped at 24. It's a radius, it's a distance. It should go beyond 24 quite clearly, but it's been capped there. So I can use CRIM to predict RAD, but I can't use RAD to predict CRIM very clearly. And so this tells me I should go back to whoever generated the data and say, why have you capped the data? This is non-informative. I'm losing a relationship here. Can we find an alternative data source? Can we uncap it and go back to the raw data? And I think that this would help us to identify poor sources of data that come in for early analysis and help us to prioritize things that need fixing rather than discovering it way down the line when you're just laboriously digging through all of your data. So the final point I want to mention is this notion of a data story. So 1 minute, okay, well, I better wrap up on data stories. Data stories introduced by a colleague called Bertel in London. He was asking, he wrote this Read Medium piece on bad data and what does it all look like. And at the end of this really interesting story on bad data, he talks about data story as a way to present the story of our data. So what are the relationships in our data? What looks good? What looks bad? What can we trust and what can't we trust? And perhaps even what could we do with this data? So if we can start to generate reports based around our data very quickly and easily using off-the-shelf tools, and this presentation is a presentation run from a live Jupyter notebook, so it's an artifact that I can put into GitHub. I can generate a PDF report from it, and you could rerun it on a new data set or an updated way of manipulating your data and generate a new report. Then all of a sudden you've got a data story telling you something of interest and telling you what you might do with the data. So I'll conclude there. We've looked at a bunch of tools that hopefully help us to understand the relationships in our data and a way of prioritizing some of those relationships in the data for investigation. That's a new tool. I'm super interested in hearing your feedback about it. Maybe you think it's rubbish. If so, come and tell me. Tell me it's not useful to you and tell me why. Or tell me what else it could do that would be more useful to you from situations that you've had. I'm super keen to get some feedback. And I think, given time, I should probably just wrap up there. Thank you very much for listening.
So if you have any question about model introspection and whatnot, you can approach Ian.
I'm nicely visible and I'm happy to chat over lunch.
Thank you, Ian, again.
Thank you all.